This is the beginning of our last unit, Unit 3, and this unit will be devoted to the topic of meteorology and weather. So Chapter 16 is going to be all about the atmosphere, its composition, its structure, temperature, and also different heating mechanisms in the atmosphere. This chapter will be split into two as per the schedule. Okay, the beginning of this chapter talks about the difference between weather and climate. So weather. This is what's happening currently right now. So when you look outside, if it's sunny out, if it's raining, that's your current weather situation. This doesn't tell you anything long term about your specific area. It just tells you what's happening over a very short period of time. And your weather is constantly changing. Your climate, on the other hand, is over a long period of time, and this is more generalized for your particular area. So Scranton, Pennsylvania, as an example, it's actually in a subtropical climate. And what that means is it's not quite a tropical climate, but in the summer and spring months it can get rather warm and humid. And then it also means in the winter months, and specifically in Scranton, we're north of the Maryland-PA border, which is generally the area that they demark as a place where people tend to get more snow if you're above that line. So our climate here, we can have snowstorms, but we could also be really warm in the summer. So there are elements of the weather and climate. So things that could affect it include temperature, humidity, cloudiness, precipitation, air pressure, and wind speed and direction. All right, so let's start talking about the atmosphere. All the atmosphere it's a combination or a mixture of different types of gases. The major component of our atmosphere is nitrogen. It makes up about 78%, with oxygen being the next biggest at 21%. And then there are small trace amounts of many other different types of gases, including helium, hydrogen, neon. But for the most part, it's nitrogen, oxygen, followed then by carbon dioxide and argon. There is water vapor in our air, and it's up to about 4% of the air's volume. And because there's water vapor in the air, this is why the atmosphere is able to form clouds and also precipitate moisture back down to the Earth's surface. The water vapor in the atmosphere is also responsible for absorbing heat energy from the Earth. There are also aerosols in the atmosphere, and all an aerosol is a tiny solid or liquid particle. Water vapor can condense onto solids. Aerosols also reflect sunlight, and they help color the sunrise and the sunset. Some other components of the air include ozone. So all ozone is a molecule of 3 oxygen atoms bonded together. The distribution is not uniform. Certain areas have more ozone than others, and the ozone is mostly concentrated between 10 to 50 kilometers above the surface of the Earth. So what the ozone does, it absorbs a lot of ultraviolet electromagnetic radiation coming from the sun. And human activity is depleting this ozone layer by adding what are called CFCs, or chlorofluorocarbons, to the atmosphere. These CFCs tend to deplete ozone, and you can understand how that could be a bad thing. If we deplete the ozone in our atmosphere, it's going to stop the ability of the Earth to block UV radiation from the sun. And if we have more UV radiation coming down to the surface of the Earth, that could have detrimental effects to humans. All right, so we're going to move on to the structure of the atmosphere. So the atmosphere has many levels, and we'll cover those soon. But what we have to understand first is how we define pressure as it relates to the atmosphere. So I defined pressure a while back, a few chapters ago. It's essentially the force that's being exerted on some amount of surface area. So if you want to think about the atmosphere as being composed of air, if you were to, let's say, just look up, the pressure that's exerted on your face when you look up at the atmosphere is essentially the entire weight of the air above you in the same sized column of air as would be the surface area of your face. Basically, you would take all of that force and divide by your surface area. So the pressure is just simply defined as force per unit area. So the average sea level pressure can be expressed in a few different types of units. So it's slightly more than 1,000 millibars, and then maybe a unit they might be more familiar to, 14.7 pounds per square inch. But our bodies are so used to the atmospheric pressure that we don't really notice that there's a force being exerted at all. And pressure also decreases with altitude. So if you think about it, as you go higher in the atmosphere, there's less air above you, so there's less of a force pushing down as you increase in altitude. And 1/2 of our atmosphere is actually below 3.5 miles, where 90% of the atmosphere is below 10 miles. So it rapidly decreases as you go up. In fact, here's a plot showing you the pressure in millibars on the horizontal axis versus your altitude. So as soon as you reach about 8 kilometers, the pressure tends to decrease very rapidly after that. All right, so let's move on to the layers of the atmosphere. The bottom layer is the troposphere. This is where most of our weather takes place, and in this layer, temperature decreases with altitude. So it gets cooler as you move higher within the troposphere. The thickness varies, but it's about 12 kilometers high. And this there's a boundary between this layer and the next layer called the tropopause. After you go through the tropopause, you would enter the stratosphere, and this is about 12 to 50 kilometers. And what's interesting about this level is the temperature increases as you near the top of the stratosphere. The outer boundary between the stratosphere is called the stratopause, which borders the mesosphere, which is the next layer, 50 to 80 kilometers. And the temperature decreases in this region. Then you would hit the mesopause and then finally go into the upper atmosphere level called the thermosphere, where there's no well-defined upper limit, and there's only a fraction of the atmosphere's mass in here. And gases in this region move at very high speeds because you're at the boundary between space and the Earth's atmosphere. And this is just a picture showing you how the temperature changes with respect to each level of the atmosphere. And you'll notice the aurora borealis that I spoke about, I believe it was in chapter 23 when we spoke about the sun. This occurs in the thermosphere level of the atmosphere. And you'll notice most of all of our weather happens in the troposphere, and you'll see that's where in this picture they're labeling where the clouds would be located. And again, it's all mostly happening in this tropospheric region. All right, one last thing for this first part 1 of chapter 16 would be the relationship between the Earth and the Sun. So we know the different types of motions the Earth has from a previous chapter. So it rotates on its axis, and it also revolves around the sun. The result of this are changing seasons. All right, so we have the sun being highest in the sky on the summer solstice, so one particular day during the summer, and then it's at its lowest point, or when we have a shortest day, at the winter solstice. We also, depending on where you are on the Earth, have different angles at which the sun rays impact onto the surface of the Earth. So somewhere in tropical regions near the equator, the amount of sunlight that comes down to the surface impacts the ground at a 90-degree angle, so perpendicular to it. And then as you decrease in latitude, the angle becomes smaller and smaller until the angle at which you're impacting the surface is 30 degrees or less, and those areas generally tend to be the opposite of tropical regions, so we would call those Arctic regions. So the seasons are caused by Earth's changing orientation with respect to the sun, and we also know that the Earth is tilted on its axis. So that means when the northern hemisphere is experiencing what we would call winter here at our location in Scranton, the southern hemisphere would be experiencing summer, and everything is opposite, vice versa. Except when we're talking about the fall and spring equinoxes, everything is the sun's vertical rays are located at the equator. So basically both sides of the equator are experiencing the same seasons. And then special days, we have summer during June 21st and 22nd in the northern hemisphere, and then we experience winter winter begins December 21st and 22nd in the northern hemisphere. All right, that's the end of this first part of chapter 16.